Good afternoon. I'm Marion Small. If you are not sure who I am a former Maritimer who is now living in Ontario. And I was happy to talk to you about how you might meet the needs of all of your learners, both the struggling students and the stronger students all at one time. So we'll spend about an hour talking. The focus will be on kindergarten to grade 8. I am full screen, so I'm not looking at the chat, but I will take little stops so I have a chance to look in case you have something that you want to say to me. I do have the captions on. I hope that's not distracting to you, but might help some of you. So one of the things that we talk about in math are activities that what we call low floor, high ceiling. So what that means is that a low floor means that almost any student could find some way to access that particular activity or problem. But high ceiling means that we can stretch kids. It's not just that they kind of do it okay, it's that they can learn even more because of the nature of the activity. And I think that's exactly what we need to do to meet the needs of all of the students we teach. We want everyone to get something good out of the particular activity. I think it doesn't even matter what grade you teach. The same thing would be true whether you're teaching kindergarten or grade 1 or grade 8. And one of the things I'm hoping you'll notice is that if you have what I'm going to call a rich activity, it's actually helpful to you because you'll have less work to do in planning. You have one thing that will work for lots of students, and that's valuable. It means you don't have to plan a whole lot of little things for different students to do. So we're going to see many, many examples. I've chosen to make a number of them manipulative based because we still want students to use manipulatives. They aren't all that way, but many of them will be. And I've used a number of virtual manipulatives because we, of course, have been living in that world for a little bit. And you can see the value should we have to go back to that situation. So let's start with younger grades. I hope you're all familiar with 10 frames. So a 10 frame is a 2x5 grid. So it has 10 little cells in it, and you put counters in them to show all the numbers up to 10. And usually we do in a pretty consistent way. We fill the first row one at a time from left to right. Then we fill the second row one at a time from left to right. So here's a problem. You used 10 frames to show a number. You filled a few frames and more than half of the last frame. What number might you be showing? So if I gave this problem to kids to do, they would all have 10 frames in front of them. They would have multiple 10 frames in front of them, not just one. I would give them counters so they could fill those frames, or we could do it virtually. And I am going to show you a picture that's virtual. And the question is what we call an open question because there are many right answers. There are wrong answers as well, but there are many right answers. So what number might you be showing? So just think for a moment what you think it might be. You don't have to say it to anyone. You filled a few frames and more than half of the last frame. So it could be that students did something like this. I don't know if you've seen this particular virtual manipulative before. Cool Math for Kids has 10 frames, which are kind of nice to use because you can fill them with different sorts of creatures. You can see that I've used a little cat, but there are little monsters and birds and apples and so on. And you can fill them one by one, or you can fill 5 at once or 10 at once. So it's actually quite convenient. So for me, this would be a perfectly respectable answer for a few 10 frames being filled and more than half of the last frame. And I would hope that the student could tell me it was 36. And that's just one possible answer. Then I want to follow it up. So kids will have done some things, and I could say, so what was your tens digit? Do you think everyone has the same tens digit? And I'm hoping they realized that when I said a few 10 frames, it meant that they might not all have the same digit. Maybe some of them had 3 10 frames full, but maybe somebody else decided that a few could be 4, and that would be okay too. Or maybe someone decided it would be 2, and we should be able to live with that, even though some of you might balk at that. So kids can do that. So what could the first 10 digit be? And I'm hoping our conversation will lead all kids to see it couldn't be like 9, because that feels like too many. That's not a few. Maybe it's a littler first digit. What could the ones digit be, and what could it not be? So if you recall, I said the last 10 frame was more than half full. So some students might decide that there are 6 in that last 10 frame. Someone else might choose 7 or 8 or 9. There could even be a student who chooses 10, and that would lead for an interesting discussion, because some kids won't like that because they are all full, and other kids could like live with that. So we're letting kids see how the tens digit makes a difference in a number, and we're letting kids see how a ones digit makes a difference in the number. They're all participating. Almost any kid could just take counters, fill some 10 frames, and fill more than half of the last one, and just tell you the number. So that's the low floor. But the high ceiling is when students think about what are the possible tens digits, what are the possible ones digits, what is like not okay. So it's not a complicated task, but I do think it has a lot of richness to it. So you could be thinking about what you like about the task. I think I've mentioned to you what I like is the low floor, high ceiling. I like that kids are physically active. I like that they're seeing visual representations of a number. I think it has lots of potential for follow-up questions. So I might say, well, suppose I filled less than half of the last frame. Will the first digits change? Will the second digits change? Suppose I filled exactly half of the last 10 frame. Then are there as many possible numbers? So there's lots of follow-up. So when I'm showing you tasks, I want you to be thinking, and there's always follow-up. That's what makes it rich, and that's why they're so great, because you don't have to plan a million things, because you can pull a lot out of one task. Here's a different question, also about tens frames. You're doing an addition, and you're showing the addition by using tens frames, and you're using the frames to actually help you figure out the answer. So in order to help you figure out the answer, I just would say it more dramatically, like I was watching Sophie do this, and I noticed she moved 3 counters from one frame to another frame in order to do the addition. What addition do you think Sophie might have been doing? So kids have the 10 frames in front of them, they have the counters in front of them, and they're going to play around. So they get lots of play around time to see what they would do. They try to put some things there. They do some addition, so they're practicing addition. So all kinds of good things are happening. Now, my goal is for them to see that if I had a question like this one, 17 plus 14, one of the things I might do is move 3 of the counters from the last frame that has 4 to fill the second frame that has 7. And then I could quickly see the answer is 10, 20, 31. So it would be really nice in a question like 17 plus 14, because you're changing it to 20 plus 11, which is easier to see. So in this particular case, that's kind of what I'm hoping will come out. You might be wondering, will it come out? And it usually does, although there are, of course, no guarantees. But then what else am I going to ask? I might ask a question like this. Why do I think Sophie probably was not doing 40 plus 8 and moving counters from one frame to another? And I'm hoping a student will say, well, the other frames are all full. There's no place to put it. Or maybe they'll say, well, what's the point? You can already see that it's 48. So different students will kind of let you in their heads and see what they're thinking. You might ask a question like this one. Why was it probably not 44 plus 12? Because if you look at 44 plus 12 and you imagine 4 full frames and 4 ones, another full frame and 2 ones, why would you move 3 out of the last frame? It just doesn't seem to make a lot of sense. Like, it doesn't help you a lot because A, it's easy to see the way it is, or maybe I would probably move 6, or I would move, they would say different things. It might be a different answer than for 40 plus 8. You might ask, why would you ever move 3 counters? And you'll hope students notice that if you had something like 27 or 47 or 37, moving 3 counters is nice because it fills a frame and we can count by tens so much more easily. So that's what we're going for. So I'm going to go to a new problem now, but I'm just going to re-emphasize that the goal again is to start with a given problem and to enrich it by getting more out of it. So I could ask a question like this one. You make yellow stacks of 5 cubes and red stacks of 8 cubes. So you have linking cubes, whether they're virtual or real. You stick them together in either yellow stacks of 5 or red stacks of 8. The rule is you can't split the stacks up, like you could pretend they're glued together or whatever you need to pretend so that you can't break them up. And then the question is, how would you show various numbers? So how would you show 18? And I'm wondering if kids realize that to show 18, a smart move might be to show a yellow stack of 5, another yellow stack of 5, and a red stack of 8. That's a way to show 18. I might ask how to show 32. And I'm wondering if kids realize that I might do 8 and 8 and 8 and 8, which is 4 red stacks. Then I might say the more interesting question, what numbers can you not show if you're not allowed to break up the stacks? So I want to give kids time for this, and I should give you time for this, but I'm not going to give you very much. And I hope you realize that there are a lot of numbers you can't show. For example, you can't show 1, 2, 3, or 4 because the smallest stack you have is 5. So that's a no. You also have no way to show 6 or 7 because you have nothing between 5 and 8. So kids can play around and find out there's a lot of numbers you can't show. So I've mentioned 1, 2, 3, 4, 6, and 7 don't work. It turns out 9 doesn't work, but 11 does. 10 does because you have 2 5s, but 11 again does not, and 12 does not. What about 13? Aha, I think you can show 13 because it's 8 and 5. So 13 works. What about 14? And kids think like that, and you let them go for as long as you think is appropriate. I think one of the things you're learning is that they're practicing a whole lot of addition, but they're doing a whole lot of what I would call reasoning. So one of the processes in the curriculum is reasoning, and they're doing a whole lot of reasoning here about why is 16 possible but 17 not? Like there's no way to get 17. Why is there no way to get 18 and 19, but maybe there's a way to get 20? So all of those kinds of things get kids thinking a lot about number, develop a lot of number sense. So this particular activity would probably last a whole period if you wanted it to, a whole math session. Honestly, you could use it in quite a few grade levels. So I could see a grade 2 teacher using this. I could see a grade 3 teacher using this. I could even see a grade 4 teacher using it, even though we tend to add bigger numbers in grade 4, because we're actually practicing multiples. Like we knew that 20 worked because it was a bunch of 5s. We knew that 32 worked because it was a bunch of 8s. So we're practicing a lot. Here's a different question. And in this particular one, I'm using square tiles. How many little tiles can you use to create a bigger square? So imagine you have little square tiles. So there's square tiles. and you want to make a bigger square out of them. Could you use 2 tiles? Could you use 3 tiles? Could you use 4? So kids have to, again, just like in the last question, experiment. What can I use and what can't I use? So here's an example that you could use 9, because when you use 9 littler red tiles, you create a bigger square. Could you use 10? Could you use 11? So do you see that as kids are playing with this, they're going to learn a lot of stuff. So imagine starting with the 9. Well, if you had a 10th tile, it's not going to work. And if you had an 11th, it's not going to work. And they start seeing it's not until I go kind of all the way around, which means I'm adding 5 more tiles. Did I say that right? 1, 2, 3, 7 more tiles, excuse me, to make the next square work, so that they're going to learn a lot of things about what we call square numbers. Staying with square tiles, this is quite a different question, and this is about fractions. So I might ask kids to create a square tile design that is 3/4 yellow. So what kind of design would it look like if it was 3/4 yellow? And I want you first, just in your heads, to imagine what it looks like, the one you're thinking about. So you have all kinds of colors of tiles. You can have yellow and red and blue and green, but you only want it to be 3/4 yellow. And when I say a square tile design, I don't mean you're making a square. I mean you're using square tiles to make a design. And so a kid might do something like this, which is the very nice, simple one. So this is what I would call the low floor. Like a kid just does something nice like this. He knows what 3/4 looks like, or she does. Make it 3/4 yellow, use any other color in the other space. And that is a question I would use for follow-up. What would the other piece be? What fraction of the design? What color could the other piece be? So we could ask questions like that. But you'll also have kids make more complicated designs. So this kid is showing me that they realize that 3/4 is also 6/8. And I'm going to ask how they know it's 3/4. And maybe some kids will tell me they know it because they know 3/4 equals 6/8 because you do something to numerators and denominators. But maybe a kid will tell me, well, there are 4 columns of squares and 3 of the 4 columns are yellow. So that makes 3/4 yellow. So you have lots of discussions in this case about equivalence and why fractions are equivalent. So this might be a nice task when you're dealing with equivalent fractions, whether it's grade 4 or 5. Staying again with square tiles, but going in a different direction, I might ask, what size rectangles can you make with exactly 20 tiles? And how about 19? So essentially, I am working with the concept of prime versus composite. I'm working with factors of 20, because if I made a rectangle with 20 tiles, the length, the number of rows and the number of columns have to be a factor of 20. But with 19, there's only one rectangle I can make. With 20, there's a 4x5, there's a 2x10, there's a 1x20, there's more. So this might be a nice task when you're talking about primes and composites, when you do that, for example, in grade 6. One more question, I think, with square tiles. You make 2 rectangles with square tiles. One of the rectangles is half the area of the other. Is the perimeter also half? Like, is the perimeter half of the perimeter of the other? Or if it's not, like, what fraction is it? So I've actually done this activity myself not too many years ago in a grade 6 class. And it was amazing to see that it was actually some of the most struggling students who came up with ideas here quicker than some of the other students. It was really marvelous. So this is an example of that low floor. Because it's hands-on and kids can just do it, they start seeing things, even if sometimes they seem to be students who struggle in math. So here's an example of one. Do you see my red rectangle? And then my yellow one is half the area. And what the kids in the room I was in did is just like literally split the red thing in half. They just like pushed half away, which is a logical thing to do. But then they had to figure out what the perimeter is. So when they count the perimeter of the red rectangle, notice that it's a 6 by 2 rectangle. And so the perimeter is 6 plus 2 plus 6 plus 2, which is, 60. And if you look at the bottom perimeter, it's a 3 by 2 rectangle. And so the perimeter is only 10. And so the fraction of perimeter relationship is 10 to 16, or 5 to 8, if you want to say it that way. And it's not half. In fact, it's more than half. So then the kids wanted to know, well, could it ever be half? Or is it always more than half? Or is it only sometimes more than half? And so they experiment some more. And that's a great question to ask. Like, is it always more? Could it be less? Like, what could it be? Here's another example where I have quite a long red rectangle, 2, 4, 6, 8, 10, 12 squares. The perimeter of that one is 26. If you look at the half rectangle below, it's 6 by 1. The perimeter of that one is only 14. So the relationship is 14 to 26. So it's not half. So the idea is to kind of experiment and see what really can happen. And as I said, it was interesting to watch kids who often struggle. They struggled a little bit with saying fractions like 14/26, but they didn't struggle at all with saying whether it was more than half, less than half, or half. And that really is the crux of the problem. So I was pretty happy. For students who are needing more challenge, so you want the high ceiling, we want them to discover, well, how big could that fraction be? Could you get like super close to 1, or are you super close to a half? Like what are the constraints? Could you ever be less than a half? And so some kids will take it as a challenge, the high ceiling students, and do more with it. And the low floor students will come to great conclusions as well. I did have one more square tile question, sorry. This one is about making a pattern with square tiles. And the rule is that it has to be a pattern, and you have to use between 30 and 50 tiles to make the first 5 terms. So you're starting to make your pattern with tiles, so you just experiment and make a pattern. But the deal is you got to use kind of a lot of tiles in that first 5 terms, between 30 and 50, or else that's not a pattern I want to see. So kids, experiment. Now, maybe kids do this pattern, which is a nice pattern because it goes 1, 2, 3, 4, 5, but it doesn't meet the rule of using the 30 to 50 tiles. If you count all my tiles here, I only used 15 tiles, so that's not enough. So then kids have to think, now what do I do? And that's where the good stuff happens. So maybe one kid realizes, well, if I've used 15 and I need to get to 30, what I'll do is just like double everything. So that is a kid who can think like that. But there's another kid who's just more practical, and they just like add 1 tile to each thing. Nope, I'm still not at 30. And then they add 1 more tile and they just kind of keep pragmatically doing it until they get their pattern. Those kids are benefiting from the task too. They're doing lots of experience with skip counting. They're kind of learning that when you add 1 thing to each of the 5 terms, you increase the whole thing by 5. So a lot of good things are happening for all students. Another tool that we found very effective for kids to use are Cuisenaire rods. Some people call them colored rods. Sometimes they are marked so you can tell how long they are. Sometimes they're solid. I'm going to show you a picture of solid rods. And what they look like is this. And what kids are supposed to do is figure out the lengths of all the rods that they see. If I decide that the light green one is going to be called length 3. So if I call that 3, what would you call red? What would you call white? Whatever it is. So I've done this with kids. I don't know why my purple went below the blue. That's a little weird, but this is what might happen. Oh, I know why. Let me tell you why. What I've watched kids do is they look at the light green and they say it's 3. And then they find out that 2 light greens make a dark green. So they know the dark green is 6. Then they find that 3 light greens make a blue. So that's 3 3s, so that's a 9. So they know that one. And then they have to struggle a little bit to figure out what the white and the red and the purple are. Now you might be thinking, but they already know how long those rods are. And if they do, then it wouldn't make sense to make the light green one 3. Maybe I'd start by making the light green one 9 or making the light green one 15. So you decide based on what the kids know what makes sense to do. So again, because it's hands-on, I do think it's accessible to lots of students. They might not find all the rods, but they certainly could find some of them. But it's a challenge for some students who might try to figure out all the rods. What if I decided the light green one was 12? If it were like a grade 7 class, I might make the light green one worth 5. Which is actually way harder, and you'll have to get into fractional or decimal thinking, so you could go in that direction as well. One of the things that we can do is think about concrete graphs with kids. And in this particular graph, I've created what I call a concrete graph because it's actually made of the blocks. And my concrete graph has 3 in the yellow row, 2 blocks in the red row, and 5 blocks in the green row. And I tell the kids, this graph is a graph of a design that I made, and it shows how many blocks of each color were in my design. So clearly I needed a design with 3 yellows and 2 reds and 5 greens. And so the idea is, can you make such a design? So that should be easy for most kids. So that's where I think we're going to have this low floor thing. And then we're going to do more with it. So here's an example, by the way, of what their design could have looked like, but there are many others. Then I'm going to say, now make your own design and make a concrete graph to show how many of each type of block you used. So kids are working, making their own designs, followed by their own graphs. And then we can have fun. We can have kids show their graphs to other kids, and they can guess what their designs look like. So we could really kind of make this into quite a nice, both geometric and data kind of activity. I could ask questions like this. Did anyone have a graph with the same number of shapes in every single line in the graph? Like, could you have had the same number of yellows and reds and blues and greens? Could you have, that kind of question. Did anyone have a graph with one really long line and the rest of them were short lines? So what would that kind of thing look like? Did anyone have a graph that had more than 3 lines? If that was the case, how many lines did it have? How many colors did you use? Can you guess the colors that they use? So we have lots of things we could get out of that particular activity. Here's another one where I use pattern blocks, but I use them in a quite different way. In this case, I'm asking kids to make a design with pattern blocks. So I'm hoping you can all visualize them. You just saw some examples. That is half yellow. So I'm going to give you a second to think, to see what you're thinking. And the idea is that if it's half yellow, what could it look like? And it turns out there are lots of good answers, and a lot of them are really worth following up with students. There are simple answers, again, for the low floor. There are way more complicated answers for the high ceiling. So a kid might do something like this. I wouldn't call this complicated, but it's definitely not simple. So it's a little bit complicated. So a kid might decide that here I have half yellow because like there are 3 yellow hexagons and there are the equivalent of 3 red hexagons when I put together my red trapezoids. So if it's 3 yellows and 3 reds, that's like half and half. So that would be a design. And I would probably follow that up by saying, well, could it have been even bigger? What would it look like if it was even bigger, guys? And then either you give them time to do it or you just let them talk about it, where you could put in an extra yellow and 2 extra reds. Then I might say, well, what if you put in an extra yellow and only 1 extra red? Like, is that okay? And I'm hoping they say no. And so again, I want you to keep seeing the conversation that would follow up. But another kid might do this. And I may have talked to some of you before, you may have heard me before because I've used this example before, but it's an important one. Many teachers look at this and immediately say the child is wrong, that this is not half yellow and half red. And they might not be unkind to the child and say, no, that's wrong. They might just say, but why do you think that's half yellow? Waiting for them to realize they were wrong. But it turns out they're not wrong. So the reason they're not wrong is that it turns out that even though half of the area is not yellow, half of the blocks you see are yellow. There are two blocks, a yellow block and a red block. And so half the blocks really are yellow. So you never said half the area, you just said half yellow. And this is like totally okay. And in fact, it's a good thing to come up so that you can talk to kids about the difference between half the area being yellow and half the blocks being yellow. Both are legitimate ideas. Then you could follow up with more questions. How many blocks might be possible? So if you had half yellow, could you make it half yellow if you used 5 blocks? Could you make it half yellow if you used 11 blocks? Could you make it half yellow if you used 12 blocks? Is every number possible? Could you make it half yellow but have more than 2 colors? Like, is that possible? Like, what would that look like? So I hope you see from these questions that there is like so much more follow-up. There are so many more things that you could do. So again, this is a very rich task because there are so many places to go in. A different pattern block question. A design has a ratio of 2 red blocks for each green block. So every time you see 2 red blocks, you see a green one. I just made it sort of cute. How do the areas of the red and green compare? So the ratio for the numbers of blocks is 2 to 1, but the ratio for the areas is not 2 to 1. So in this particular case, it looks like whenever there's 1 green, there's the equivalent of 6 greens worth, or 6 greens worth of red, if you know what I mean, because each red is worth 3 greens. So the ratio then is like 6 to 1 rather than 2 to 1 if you're thinking area. But then you ask, but is that always true? What if I had made a different design? Like, would it still be true? And so kids get to kind of explore a little bit more. This one is probably a little less exploration than the last one, but there's still exploration to do. Just like with the Cuisenaire rods, and I said a Cuisenaire rod was worth a certain amount, what should all the other rods be worth? I can do the same thing with pattern blocks. A green pattern block is worth 4. Make a design that is not all green. It can have green, but other colors too, and tell me what it's worth. So a kid has to think of what the other blocks would be worth if the green one were worth 4. But you can make it more complex and make the green one worth a half rather than 4. Or you can say something like, if the green one is worth a half, make a design that's worth 8.5. Now, I've actually sat in a group of grade 7 students, and I gave what I call 3 parallel tests. In one case, I told them the worth of a yellow instead of a green, but in one case, I had a yellow worth 6 for one group. I had a yellow worth 15 for another group, and I had a yellow worth a half for a third group. I let kids pick which group they wanted to be in, and then they had to make a design and tell me what it was worth. So I laid out different challenges by using what I'm going to call parallel tests, making it a little bit simpler for some kids than for others, which is, again, a way to have access for all students, but a challenge for students who seek more challenge. I could ask a question like this one. I'm making a design with blue pattern blocks, and it has less area than a design I make that has green pattern blocks. And you could just pick numbers. So could you make a design with 4 blues that has less area than a design with 4 greens? What about 4 and 10? What about 20 and 53? So kids have to experiment with what numbers could fit in the blanks to make that true. So they're working with multiplication. They're working with the idea of area as well, the ratio of area as opposed to the ratio of number. So a lot of good stuff could happen there. A new material, probably one very familiar to you, which is base 10 blocks. You model a 2-digit number with more ones blocks than tens blocks. What could that number be? So I've actually done this with a bunch of grade 2 students, and I've done it with a bunch of grade 3 students. In front of them, they have the tens rods, and they also have the little ones cubes. And their rule is it has to be a 2-digit number. So I just remind them that means that it's 10 or more, but it's not as much as 100. And it has more ones than tens. What could the number be? And so kids kind of experiment. So I've had kids say like 23 with 2 tens and 3 ones. Or they might say 37 with 3 tens and 7 ones, and so on. And then what happened to me, I'd asked this question if I needed to, but it actually happened in a classroom for me. One girl said that her number was 81. And so I walked over to the girl and said, so Sarah said that her number is 81. What do you think her design looks like? And it's interesting because a lot of kids think Sarah got it wrong because there are not more ones than tens, because 81 has 8 tens and 1 1. But in fact, what Sarah did was 7 tens and 11 ones, which is 81 and does have more ones than tens. So Sarah kind of did my work for me. If she hadn't, I would have had to have done something. But I want kids to see that there are many ways to model a 2-digit number. And a lot of those ways, in fact, have more ones blocks than tens blocks, because you could always trade your tens blocks for ones. So that might be fun to do with kids. It could be this one instead. You model a number with exactly 13 base 10 blocks. What could the number be? So again, it has a low floor because you just give kids blocks and they can count up to 13. They put down 13 blocks and they just tell you what it's worth. So a kid could put down 13 ones and say my number is 13. A kid could put down 13 tens and say my number is 130, which is a little bit more sophisticated. A kid could do a mix. Maybe they put down 6 tens and 7 ones and say their number is 67. So there's lots of stuff kids can do. And I've written some of the numbers that they might come up with here. And the reason I wrote them this way for you is that something very cool happens. If you haven't seen this before, maybe you have, what you'll notice about the numbers in the left-hand column is that if you add the digits, you get 13. And that makes sense because I said, except for the last one, which I did wrong, it should have been 148. Because you were supposed to use 13 blocks, if you use like 6 of one, you would use 7 of the other. If you use 5 of one, you use 8 of the other. The bottom 149, I apologize, should be 148. If you use 1 of those and 4 of those, then there's only 8 of the others that you can use. So those are interesting. If you look at the numbers on the right and you add the digits, you don't get 13, but you do always get 4, which is kind of cool. And so the question is, well, are there things that you could get that don't add to 13 or 4? And that's what kids would explore, especially the kids with high ceiling. And in fact, it turns out there is no other possibility. It is 13 or 4. And kids could experiment with Y. So I just want you to think about, for example, 400. The reason that could be 13 blocks is that you could have 3 flats, 3 hundreds, and 10 sticks. And that's where the 13 came from. If you look at something like 130, you could have 13 sticks. So it turns out that when there would have been what we traditionally call a regrouping, those are the numbers on the right-hand side. So kids really like this. I've done this many, many times. I've never had an experience where kids actually didn't enjoy the task. I could ask a simpler question like this one. You can represent a number with just a few base 10 blocks. Could the number be small? And I think the kids should say, yeah, like it could be 2 or 3 or something. Could it be big? And you're hoping kids realize, well, it could have been the thousands blocks. So a couple of thousands is still a big number. So this one is a much simpler one that you might use to kind of lead into one of the others. Now, this one is something you might use in grade 5 or forward. In grade 5, where we teach kids how to multiply two-digit numbers, we often use an array model. And in an array model, we're building a rectangle that has a length of 12 and a width of 13 in order to show the area, which is the product, which you call the length and which you call the width. You might have done it the opposite way. That's great. Now, if you look at the picture I created for you, and I did this, by the way, with virtual manipulatives that you can make different colors. I used a resource called the Math Learning Center and used their manipulatives. And you can color them the way you want. And so you can see on here that I've actually used 12 blocks to build a rectangle that's 12 units high and 13 units across. So the reason it's 13 units across is I used a 10 by 10, and then I used 3 more sticks. So you can look at the top and you could see, you could count that it goes up to 13 little squares. If you go down, there's 12. But I used 1 flat, I used 5 sticks, and I used 6 ones. So in total, I used 12 blocks. So I used 12 blocks to show 12 times 13. So my question for kids is, well, suppose I wanted a multiplication, but I didn't want 12 blocks. I wanted to use 18 blocks. What multiplications could I do to use 18 blocks? Now that's a rich task, but again, it has low floor, high ceiling. Here's low floor. A kid just sticks together 18 sticks. And I've made a rectangle, and I'm showing you a multiplication. If you look across, it's 8. Sorry, 1, 2, 3, 4, 5, 6, 7, 8, 9. So did I do that? Yeah, so it's 9 and 9. So I've used 18 sticks, and so it's 9 across, and it's 20 deep. So I've multiplied 20 times 9 to get 180, and that's one way to do it. But there are other ways to do it. So here's another way to do it. This one is 15 across and 12 deep. So I'm showing you 15 times 12. Again, I've used 18 blocks. If you look in the corner, I used 6 little ones. I used 7 sticks, and I used 1 flat. So kids could experiment. There will be kids who rise to the challenge and do a whole whack of them, and there will be kids who don't. And again, our purpose is to provide value for all students. The kids who don't do a whole bunch are still learning. It's still great. And they're just kind of getting at it slower. And I think that's fair because that's the way the world works. There are other kids who actually just quickly get answers and kind of sit around, and they have way more to do because there's always going to be so many more possibilities. So this is, again, this low floor, high ceiling. Another tool that I think is valuable to use are fraction strips. One fraction strip is half as long as another. So a fraction strip, I'm going to show you on the next slide what they look like. They look like this. So you can show halves and thirds and quarters and fifths and so on. So if you look at my strips there, you can see that in the line that shows 1/5, the green line, there are 5 fifths making up the 1. There are 4 fourths in the yellow line making up the 1. These are available online in a lot of different ways. They're also available kind of in print. I usually Google the word fraction tower and find something like this and print it out. So my question was, one strip is half as long as another, which could they be? So we look at our strips and kids kind of mess around. So it looks to me like a quarter is half as long as a half because 2 of the quarters are the same length as a half. It looks to me like that a sixth is half of a third because 2 of the 6 make a third. And so we're messing around with sort of fraction equivalence, fraction multiplication, because we're actually taking a half of a half or a half of a third, but we're doing it softly with the manipulatives. Now, if a sixth is half of a third, that means that 2/6 is half of 2/3. And 3/6 is half of 3/3. So I could extend the activity to make sure those ideas come out. I could do something like this one. One fraction strip is just a little bit longer than another one. What could the strips be? And you could look here and decide maybe a quarter is just a little bit longer than a fifth, or a sixth is a little bit longer than a seventh. But I could ask more leading questions. Is there anything on the top that's just a little bit longer than something sort of toward the bottom? And maybe a kid will kind of look and say, well, I think if I use 6/8, it's just a little bit longer than 2/3. So they could extend, they don't use only the unit fractions. And so that's, an extension of what I just showed you. What equivalent fractions do you see? And again, we're going to look at it and we're going to go back to the first task, but it's not just going to be halves anymore. They're going to see maybe that a third is the same as 3/9. They're going to see maybe that 2/10 is the same as 1/5. There are so many equivalent fractions they could look at. Here's one for older kids, area relationships. Draw a circle on grid paper. Make a triangle that has the same height as your circle. So essentially the height of the triangle would be the diameter of the circle. And make sure the base of the triangle is as wide as the circle at its widest, which is also a diameter. So essentially I've told them to make a triangle where the height and the base are equivalent to the diameter of the circle. And I've asked them how their areas compare. Now, you could ask this after kids know about pi r squared, but you could also ask it before they know about pi r squared to kind of lead into that. So if you actually look at the triangle and the circle, and I deliberately set them sort of side to side there, you can certainly see that the triangle looks smaller in area, but like, what is it? Is it like half? Is it like 2/3? Like, what is it? Kids mess around to figure it out. And it turns out it's actually 2/pi, which is like close to 2/3 the size, which might be an interesting problem to get algebraic with your kids who need more challenge, and stay softer, about 2/3 with other kids. There are percent questions that you might ask for older kids. Like, you buy a jacket that was 50% off, and then another percent was taken off, like it was a sale on top of a sale, and you pay $20 at the end after that second percent was taken off. The question is, what percent was taken off the second time? Because you get to choose that, but then what was the original price based on the percent that you chose? So kids have to decide what to do. Like, this is a real problem. They don't know exactly what the answer is right away. It's not staring you in the face. They need to think. So maybe a kid will say, well, it was 50% off and then another 50% off, and I paid $20. So that means the middle price was $40 and the original price was $80. So that's like a nice, simple one. But it turns out there are many other answers, maybe not as simple. It could have been that the second time you took off 20%. So if you took off 20%, you paid 80%. And if 80% was $20, then the middle price was $25 and the original price was $50. So that's more complicated. And there are things that are even worse that you could do as well. And you might even use models like double number lines to help you see why the price was $25 if 20% off was $20. So there's a lot of opportunity to use tools here as well. This was an ugly one where you took 17% off. So honestly, it could get uglier, it could get nicer. Here's a question for probably grade 7 kids. You add two numbers and the answer is a little less than if you subtracted them. What could your numbers be? And I want kids to realize that if you added less, if you add and you get less than if you subtract, I suspect you added a negative. So that's the underlying concept that I want them to think about. But it says a little less. So you don't want to add like negative 100 because then the difference will be like a lot. So the idea is for them to realize it better be a negative number that's not too far from 0, and so kids could play around with that. I'm going to talk about one more thing here, then I'm going to stop sharing for a minute in case you have questions that I should be responding to. This is about using algebra tiles. Algebra tiles are tools we use probably mostly in grades 7 and 8, but we might use them for some teachers in grades 5 and 6. And they are used to represent both the variable, whether you call it x or n or whatever you call it, and the constants. So in this particular picture, I used virtual algebra tiles, and I'm actually showing you an equation, 3x equals 10, because on the left side, I have 3 of the x tiles. The x tiles are rectangles. And on the right, I have 10 ones, because the little yellow, they're supposed to be squares, are worth 1. Now, when you look at that, you see that in total, I have used 13 tiles, 3 on the left and 10 on the right, so it's 13 tiles. But actually, the solution to the equation is actually kind of sitting there. Now, if you haven't used these before, I'll tell you why it's sitting there. Can you see that each one of the x's would have been worth 3 if there weren't that 10th one? So you can see 3 and 3 and 3. Each x is worth 3, but they have that one extra guy. So he has to be split equally among the 3 x's. So each x would be worth 3 and 1/3. So we actually solved an equation involving whole numbers that has a non-whole number solution with algebra tiles in a way that you can actually see it. Now, you can also use algebra tiles to show negatives. So you might be working now in grade 8. And this model shows 3x minus 2. And the reason it's minus 2 is I made the 2's red. So each of those little red squares is worth -1. And on the right, I have a negative x, again, because I used a red rectangle. And I used a +7. And notice that this one also uses 13 tiles. There are 5 on the left and there are 8 on the right. So if I said to kids, model an equation that uses 13 tiles and solve it, I could have the nice simple one that you saw first. I could have the more complicated one that you're seeing now. I could ask a question like this one. Use 15 algebra tiles to model an equation. What equation might you be solving? What is the solution? So all I did was change to a different number, but it's exactly the same idea. You could have simple solutions. You could have more complicated solutions. So I'm showing you there that the bottom one is nice and simple, and the top one is not as pretty because you don't get a whole number or an integer solution. I'm going to tell you one statistics question, and then I really will stop sharing and talk to you. A set of data has more than 12 values. The mode of that set of data, so that's the most frequent number, might give people the wrong impression of the data if the mode were the only information they had. So somebody tells them there's this data about salaries, and the mode salary was $1 million. So you might be thinking like most of the salaries are $1 million, but in fact, there could have been $1 million and $1 million and 5,000, $200 ones. So the question is for kids to realize the mode could be misleading, but I asked them what the values could be. I asked them to calculate the mean, median, and mode. So I'm getting them to do some work that's straightforward, but I'm also getting into concepts about why that mode might be misleading. So I have some possibilities there, and I'm going to stop sharing for a minute because I think it's better to answer questions than to keep sharing. So I will share again if you want, but I'm going to respond to the questions I'm reading now. So somebody says, what do you do with a medium to high ability student who always goes for the low floor? That's a great question. So here's what's happened for me. My experience has been that they'll do it for a while and then they won't do it anymore because I don't rise to the occasion. I don't get angry with them, so it's no fun anymore, so they don't do that. But if I did have a student who always did that, I would just privately walk over and say, like, this time, this is what you got to do. And you're like, I know you can do this and it's great. And you can do it in a positive way. Like, say, I need someone to give me like a little bit crazy answer so I can show it to other kids. Would you be willing to be that person to show me that sort of harder answer? So for me, that's always the case. I find that fewer kids do that than you would think. Most kids do seem to do what I would say is the right thing, but I admit that it doesn't always happen, and there might be kids that you have to talk to. Is there, I mean, I can go back to my slides, but I want to see, are there any other questions that anyone wants to put in the chat to respond to? I'll give you another minute or so, and if you don't, I will just show you more slides until our time is up. Okay, it looks like no. So I'm going to share my screen again. And we'll just go until our time is up. Okay, so this one is a geometric task. A triangle with a vertex at 2, 4 is reflected. The resulting triangle has a vertex at 4, 2. Where could the original and final 3 vertices be? So I'm just going to show you where the vertices are. So the original one and the final one. And you have to somehow do triangles and make a reflection happen. So this is interesting because I think there are some soft ways and there are some more complicated ways to get into the task. So here's what I would say is a more complicated way. Where did my soft way go? There it is. And there's my softer way. So look at this one versus look at this one. And so there are again appropriate challenges because kids can do what they can handle, but they're also learning from the kids who do something different than what they did. Here's another geometric one. 2 of the vertices of a quadrilateral are 1, 3, and 5, 3. What kind of quadrilateral could it be? So here are 1, 3, and 5, 3 on my little graph. So imagine in your head now that those have to be vertices of a quadrilateral. Just imagine what your quadrilaterals could look like. There's quite a variety. And what I get kids to do is make sure that the other vertices are on lattice points so that they can read me off the coordinates, and they're practicing coordinate reading. So it could be something like this, but it could be something like this, but it could be something like this. So kids get to kind of play around. There could be a question about volume. One prism's volume is exactly 50 cubic centimeters more than another prism's. What could their dimensions be? So kids are practicing volume, and they could make it more complicated or less complicated. I think sometime if a kid realizes that if it's, you could think of having a prism and just stick 50 on top of it, and that would be the extra 50. So they just make up a random prism, and they just make sure that the extra part is 50. So if they can come up with one prism that has a volume of 50, they just kind of stuck it on top of another. So there's lots of possibilities that kids could come up with. This is more of a grade 8 kind of question. You multiply 2 integers and the answer is about 50 less than one of them. What might the integers be? So you multiply 2 integers and the answer is 50 less than one of the integers you multiply. So here's what I'm hoping kids think. Well, if I multiply 2 negatives, the answer would be positive. So that's more. So I didn't multiply 2 negatives. Now, could I have multiplied 2 positives? And then they start thinking about that. But when you multiply 2 positives, is your answer usually less than the numbers? Well, not usually. But then there is that 0, guys. So there might be something you could do. So probably one is positive and one is negative, and they kind of mess around and figure out what it could be. And there are, in fact, multiple answers, like 1 times negative 49, which is exactly 50 less than 1. or 2 times negative 24, which is negative 48, which is exactly 50 less than 2, but it didn't even have to be exact. It could have been 2 times negative 23 or something like that. It could be one of these more interesting sort of Fermi tests about how many text messages would a kid send in a year. And that's a big problem for kids to work on. And this is something that would certainly do in groups, not individually. So I'm looking at my watch and it looks like we have no more time, which is perfect, because what I was saying is that I'm looking for tasks that encourage thinking, not just doing, and often encourage generalizations. And I think we're going to leave it at there. So it was interesting. It was hard not to be able to chat with you, but it was hopefully useful to you. And I'm sure that you'll have that stream available to you to look at in the future. So have a good afternoon and goodbye.